Everyone, so in this short video I want to talk about a really cool math operation that we can use in Houdini that is called the modulo operation. The cool thing about it is that we can't just use it in Houdini, we can use it, in every programming language, including Vex, of course. We can use it in spreadsheets, we can use it in anything really. There are many other use cases outside of Houdini for this, but in Houdini we want to control with this now how to or when to emit certain points. Later on, we will also use this, by the way, for RBD simulations and all that, so just keep the concept in mind. What we already know is that we can control when something is emitting with an expression, and for this I this time don't use the constant birth rate. Let's use the impulse count and set it to, I don't know, 500 maybe, and let's press start. So every frame there will be 500 particles. Maybe 3 times more. Yeah, something like that. And currently it just, falls down, nothing surprising. Let's control our impulse activation here with an expression we already know. We could say, for example, only emit when the start frame is equal to the current frame. So only on the first frame emit. And then we only have a one-time emission. We also know that we can say, if the current frame is, let's say, higher than, 30, then it should emit. So we don't have anything happening for 30 frames, and then all of a sudden something happens for the rest of the time. And all of this is really cool and handy, but we don't know yet how to kind of constantly emit in a certain interval. So let's say every 10th frame. And this is where the modulo operation comes in. And I want to quickly show you how to do this. $f percentage 10 equals 0. And equals with 2 equal signs, right? So if I press start now, you can see what it does. Actually, on every 10th frame, it emits particles, and in between it doesn't. So if we look at the first frame, we can see the result of this is 0. Until frame 10, and then it's 1 all of a sudden, and then for the next 9 frames again it will be 0, and on frame 20 it will be 1 again. So how the hell does this actually work? Let me go to the drawing board and explain this to you. Now in Houdini, the modulo sign is defined by a percentage sign. So that might be a bit confusing, but just remember that the percentage stands for modulo. And what we did was this: we said $f modulo 10. So let's quickly have an example of what modulo does. It gives you the remainder of a calculation. So for example, if I have 1 and I want to have the modulo from 5, what comes out of it is it calculates how many times does the 5 fit into the 1, which is 0. And then, and this is important, the remainder is 1. So this is kind of what's left over. Another example, 3 modulo of 5 means how many times does the 5 fit into the 3? No times. And then the remainder of the whole calculation, of course, is 3. More interesting it gets when we have, let's say, 6 modulo 5, because then how many times the 5 fits into the 6? Well, 1 time, and the remainder is 1, because if you take the 5 away, what's left is 1. And this is the modulo, this number here at the end, that's the modulo. One last time, the 13 modulo 5, how many times does the 5 fit into the 13? 2 times, but that's not what we care about. We care about what is the remainder, and that is 3, because 5 by 2 is 10, and if you subtract that, what's left is 3. Now let's have a look what this means when we do this on a couple of frames. And this time, to make it a bit easier, and I don't want to write too much, let's do it with the current frame modulo 5. So the current frame, let's say, is 0, 1, 2, 3, 4, 5, 6, and so on. Then the modulo result, and keep in mind there is no equal sign at the end, it's just the modulo if you would use it directly. So what would we get? The remainder is here 0, because 5 doesn't fit into 0, and the remainder is 0. Same for 1, and for 2, it doesn't fit in, so the remainder is directly 2. Remainder here is 3, remainder here is 4, and here it becomes interesting. How many times does the 5, the frame, fit into the 5? 1 time. How much is then left? The remainder is 0. Interesting. So if we go on, okay, for the 6, it fits in 1 with a remainder of 1. The 7 fits, or the 5 fits into the 7 again 1 time, but the remainder of that will be 2, and so on. So for the 8 it's 3, for the 9 it's 4, and then the 10 again, the 5 fits 2 times into the 10 with no remainder, so it starts at 0 again. And here you can now start to see finally the pattern, I hope. It always goes through 1, 2, 3, 4, and then it starts at 0 again. So it repeats itself. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0. And the interesting thing is what we now did is actually not $F modulo 5, but we added something to it. We said if the result equals 0. And actually, to be very precise, you would have to put this into brackets, or actually parentheses, to be precise. And what this means is that the result of this that we have calculated up here will be compared to the number 0, and then the result of that will be, so let's see, the result of the $F modulo 5 for the first frame was 0, therefore it is equal to 0. So the result here will be 1. Is the next result equal to 0? No. Is the 2 equal to 0? No. Is the 3 equal to 0? No. Is the 4 equal to 0? No. Is the 0 equal to 0? Yes. And here you can see what's happening. If we then compare the result, which is of course also a pattern that repeats itself, then we will come out with this interesting activation pattern of, okay, it activates, then for 4 frames it stays on 0, then it activates again, for 4 frames again it stays 0, activates again, and so on. So this is the whole idea behind the modulo, that we use the fact that the modulo gives us back the remainder, and we compare the remainder with 0, which should only happen, you know, once every times we put in for the modulo. So, you know, don't worry, you don't have to kind of overthink this every single time you use it. It's always this logic here, and that's easy to remember, right? $F percentage, the number I want equals 0. Very easy to remember. I just wanted to explain how it works. And this is why this worked, because only every 10th frame, the result of the modulo is 0, and then it only emits every 10th frame. And we can change this, of course, so maybe every 5th frame should emit. It's also, of course, possible, then it's faster, surprise. And technically, like we said, if you want to be absolutely, you know, correct, you would have to put this into parentheses. This would be a bit cleaner and a bit easier to understand if someone else reads your expression. But technically, you know, it works without the parentheses, and that's why it's a bit faster to leave it out. And the cool thing is that also works completely outside of a pop simulation. For example, if you have a switch here between a box and a sphere, whatever, you could put in here an expression that says, you know, give me the first input every 5th frame. So I take F modulo 5 equals 0, and I think now it's exactly the opposite. It looks like this. We have, you know, the box every 5th frame, and if that's not the case, we have the sphere. So it doesn't really matter where you use it. It's just a really handy little tool to create intervals, and this is super helpful if we want to, you know, create this for emitting stuff in our pop simulation. And later on we will see we can use the same technique in any other solver as well, be it Vellum or be it Flip simulations or Pyro or whatever. We can use this for all kinds of stuff. So as you can see, pretty cool thing. So I hope this is helpful. Thanks very much and see you later. Cheers.